Hello to everyone, it's Eugene. This film adds to small collection of my devices for my home lab, and here I will tell you about a construction which allows measurement of saturation current of chokes, transformer windings and other inductive elements. Okay, let's go. To begin with, a little history of the issue. What is saturation current and why is it so important for us? Let's imagine any transformer. For example, this figure shows a transformer of a flyback converter. A power switch is installed here, which opens and supplies voltage to the winding. According to the law of induction, a linearly increasing current occurs in the winding, and the rate of its growth is directly proportional to the voltage applied and inversely proportional to the inductance. This current grows and grows, and until at some point of time the field strength generated by the windings leads to saturation of the ferromagnetic core of our transformer. Of course, it is correct to talk about saturation induction here, and besides, not the current itself works, but so-called ampere turns, i.e. The less turns we have, the more current we need to form the saturation field. But we will not go into such details, and the only things that matters is that in the saturation state the ferromagnet loses its ability to absorb field lines, and its magnetic permeability drops sharply. So at this point the inductance of the winding drops, and accordingly the current begins to increase avalanche-like. At the same time, there are a lot of unpleasant moments. Firstly, a drop in the magnetic permeability of the core leads to a loss of magnetic coupling between the windings, and therefore the efficiency of the transformer immediately decreases. Secondly, surge of current gives rise to completely unnecessary ohmic heating of the winding. Finally, the transformer in the saturation state begins to generate strong electromagnetic interference in the surrounding circuits. From all this, it's obvious why designers of voltage converters try to avoid saturation of induction elements. Although, stepping aside a little, it should be noted that there is a variety of converters in which saturation is a necessary component of their operating mode. These are so-called blocking generators. The simplest circuit on one or two transistors often found in internet and recommended as the cheapest and easiest to manufacture. In their design, core saturation is necessary to close the power switch. From what I said above, it is clear that blocking generators cannot have high efficiency, so I don't really like working with them. Okay, so we need to avoid saturation of the core. But if we want to build a converter with a high power density, i.e. to use the inductor as efficiently as possible, then it is necessary to pass the maximum current through it. Therefore, it is necessary to work in the range of current high enough to develop acceptable power, but in no case introducing the core into saturation. I hope it became clear from everything I said that measuring the saturation current is an important task. And now I will show you the device with which I do this. The principle of measuring the saturation current is very simple and is based on the theoretical assumptions described by me in the previous part of the video. A voltage is applied to the tested product,
and the current flowing through it is measured using a series connected current sensing resistor. Since the saturation current can reach units of amperes or more, the voltage has as a rule a pulse shape with a fairly large duty cycle, and the measuring resistor has a nominal value of order of ohms or less. The duration of the voltage pulse gradually increases until a characteristic break appears on the current waveform, and the current value at this point is the saturation current of the transformer or choke under test. I found several articles in internet where the authors described the creation of similar devices. All of them are arranged in a similar way. There is a certain master generator with an adjustable pulse duration, an amplifier stage, and a current measuring circuit. One of the authors tried to build an automated meter based on a microcontroller that would select the desired signal duration itself and display the resulting saturation current value on the built-in display. But he faced serious problems. The fact is that the described measurement principle itself is based on extremely subjective criteria. Determining the breaking point on a current waveform is quite difficult to describe in algorithmic language. Among other things, the signal usually has a very noisy appearance. As a result, I found this method too complicated and preferred to use the simplest approach using a separate oscilloscope. So, this device is not an independent, completely autonomous matter, but a kind of attachment to a digital oscilloscope. I have had such an scope for a couple of decades, and it works under Windows 98. But in principle, any other oscilloscope will do, up to the most ancient models with a cathode ray tube. Okay, the tester circuitry is also extremely simple and is based on conventional 555 timer. It is connected as a high-duty rectangular pulse generator. The pulse duration is regulated by these potentiometers of two different nominals. This allows to expand the range of precise adjustment. Current measuring resistors also have three different nominals switched by jumper: 10, 100 and 1000 milliohms. It makes it possible to measure currents from tens of milliamperes to hundreds of amperes. This small N-channel transistor has a protective role when current and consequently voltage of these resistors increase up to 2 or 4 volts. It opens and fastly discharges our time setting capacitor to 0, so it breaks the cycle of the timer. A special feature of this circuit is use of p-channel power MOSFET as a switch, which allows it to be controlled directly from the timer output. The fact is that the timer in a standard circuit generates pulses with a fill factor of at least 50%, and in case of using conventional N-channel switch, these signals would have to be inverted somehow. This is a demagnetizing diode. I used Schottky diode. Any powerful diode will work. The powerful part of the scheme is fed from this capacitor, 22,000 microfarads. Any other electrolyte capacitor will do, of high enough value. Its role is to supply high current pulses, so it must have big capacitance and low ESR. It is charged from this resistor. This is simple protective circuit of containing fuse and inversely biased diode, and all the scheme is powered from 7815 linear voltage stabilizer. And this diode only shows when the scheme is on, which is connected by this switch, on-off switch. So that's all. Let's look how it works in reality. Okay, this is the device. I used simple two-sided PCB and etched it in a rather rude way. All active components are on the upper side and all passive is under the board. I also etched all the foil near the components to avoid short circuits. All the upper plate is ground. It ensures low resistive ways for current. This is our trimmers, light diode, fuse, switch. This is a large electrolytic capacitor. Here are our current sensing resistors. The jumper is now set to 1 ohm nominal. All this thing is connected to 12 volts power supply. Let's switch it on. Okay, this is my scope, which I told about. This is Veliman, another old thing, maybe end of 90s, I think. It has 1 gigasample, 50 megahertz, which is some fast. I have had a long romp with this large mess because it uses parallel LPT port, which is rather a rare thing now to find. This is its software. The lower trace is the first channel of the scope. It is connected to the current sensing resistor, and the upper trace is connected to the gate of power switch. I used it to strobe the signals. Okay, let's switch on our circuit, activate our trigger, and we see some sort of signal. This is some ringing here. Oh, I forgot to say that our device under test is neon lamp transformer, which I used in some previous video. Maybe it is not very good example for testing because it has very high leakage inductance and high interturn capacitance. So I think that this ringing is because of these factors. Okay, let's trim our duration of our pulse. This is the main pulse beginning. Okay, now we have, so you see this king. This is the saturation current point. Okay, let's look. We have 0.5 volts per division. So this is something about 0.75 or 0.8 ampere, 700 milliamperes saturation current. Else two useful things we can do with this device. The first is to measure inductance of the transformer or the choke. So this slope angle gives us the inductance value. And the other thing is when emitting transformers are made, we sometimes lose the polarity of the windings. And here, if we connect the second trace of the scope to the secondary winding, we can determine its polarity. A very useful thing. Okay, this is how it works, and I will use it in my practice. Thank you very much for your attention. Bye bye.